So we've recently seen writing equations of a line in 3 dimensions using the parametric form. Now we're going to look at another similar type of graph that we might think of in the category of flat or straight or has a direction, and that's the plane. So we're going to take a little peek at the equation of plane. Now I'm going to do a very poor rendition of sort of give you an idea of what I'm talking about here. So let's suppose we have our z-axis and our x-axis and our y-axis, and we are going to imagine a plane, and let's suppose that this particular plane hits the ground here and here, and it sort of tilts backwards, and it goes in this direction. It's not vertical, so let's just say it goes like this, and I could sort of close off and make you think of it that. But let's suppose that the z-axis pops through it right here. All right. Now, when we do learn about sketching the plane shortly, we're not going to use this version of it here, but I want you to just imagine someone took a piece of cardboard or a piece of paper and tilted it back so the z-axis pokes through it. And I want you to see that there's going to be some issues talking about what direction does it go. Now I want you to imagine that we take this plane and then we lay it on this paper. All right, that we lay it on this paper. So now this paper has become my plane. So here is a vector on my paper, and 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 here is a vector on my paper. Please note they're all on this so-called plane, but they go in many different directions. In fact, we can change the word many to infinitely many directions. Having said that, there are vectors that don't stay on the plane. There's definitely vectors that poke upwards, or they go downwards. So there's definitely vectors. And so the question arises, what is it that these vectors all have in common in a mathematical sense? I mean, what they have in common is these vectors are on this same plane. But how do we mathematically describe that? And so this is a really clever little trick. And just so you know, I would not be the clever one. I'm repeating others far more clever than I. But if we were to look at each of these vectors, every one of these vectors is, I'm going to use the word perpendicular for the moment, perpendicular to a vector that sticks straight out of the paper. Remember that word? That's right, orthogonal. So this vector is orthogonal to my red pen. 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 And if you turn them sideways, every single one of them is orthogonal to the pen. What that means is, if I could figure out what this vector is, this is a vector that they all have in common. So we need the vector normal to this plane. That's the first significant math clue involving direction. These vectors have too many directions to name, but they're all orthogonal to this vector. And we could change the length of my pen. You know, here's the lid of the pen. But we wouldn't change the direction. We would only change the magnitude in that case. So we need a vector normal to this plane. And then I want to remind you that if the vectors are truly orthogonal vectors have this situation where the cosine of the angle is 90 degrees, or their dot product is 0. Or dot product is 0. Now I just want you to see something right here. The objective is to write an equation of the plane. And I've just established something that is going to turn into an equation. A dot product that is 0. So now, let me change this from sort of a visual and conversational problem to an algebraic problem. All right, here we go. Now for some algebra. So let's let the normal vector be defined by components A, B, and C. This vector is normal to the plane. And I know I've been kind of referring to it before, but there are subtle differences between the word perpendicular and orthogonal and normal. If you do a little bit of searching outside of the book, sometimes they'll define normal as it's perpendicular at a point to some sort of a surface. But there are other, both versions of that and a little bit of opinions on that. So we're going to say that this is kind of our direction. We know the vector that sticks out of the plane. Now what we need is, we need a vector on the plane. And I want it to be a random vector on the plane. It doesn't need to be a very special one. So let's suppose I have this point here, x0, y0, and z0. So that would be a point on the plane. And then I take any other random point. So let's suppose we're given a particular point and we're given a particular normal vector. Let's take another point. Let's suppose I stop right here and we'll call this point x, comma y, comma z. So this vector, I'll get out of the way in just a second here. This would be a random vector on the plane. And what we've established is, no matter which vector on the plane I choose, it's perpendicular to this vector that I'm holding if they're touching. We call those vectors orthogonal then. So, let's write this vector, this random vector. The vector that begins here and ends here. Now, for most of my previous examples, we've had numerical values and we could just count, like how far is it from x0 to some random x value? Well, that distance is x minus x0. Second minus first is your distance. Y minus y0 is your second component. And z minus z0 is your third component. Now this step-by-step demonstration will probably fade a little bit out of your higher order memory, your most used memory. The result of this is going to be quite simple, what you'll see. So here's what we got. This vector is this vector on the plane, and because x, y, and z could be anywhere, this vector is a random vector on the plane. Think of the x and y values in your equations of the line. Those x and y values represent random points. We have a normal vector, ABC. that vector is normal to the plane if they were touching the perpendicular. Because we have this normal vector concept, we know that the cosine of theta is equal to 0 when there's a 90-degree angle, because theta equals 90 degrees, in case you need that in writing. What that means is the dot product of this vector apparently I can't write and talk at the same time. So the random vector on the plane, dot product the normal vector, that should be 0. My students, this is a form of an equation. This won't be our landing point. It's a little bit separated from the world of algebra, but I want you to see there are vectors living with our algebra. And if you recall how dot product works, we distribute, not in a normal distribution, but matching components multiplied out and then added together. So we have A times X minus X0 plus B times Y minus Y0 plus C times Z minus Z0 equals to 0. This is an expanded dot product. And this, my students, is our equation of the plane. Now, when we come back next, we'll start looking at a variety of examples, starting with some pretty straightforward ones. This is algebra. The vectors no longer appear to be there because we've done the dot product calculation. But the source of this is the dot product involving a 90-degree angle. All right? Until next time.